Welcome to the Coherence Times, where we dive into the science and the story of quantum computing. I'm your host, Ryan Mandelbaum. Every other week, I sit down with researchers, technologists, and thought leaders to unravel the incredible challenges and breakthroughs shaping this generational technology. So, whether you're a tech enthusiast, an industry leader, or somebody just interested in how quantum computing might change the world, you've come to the right place. Together, we'll demystify the concepts, bust the myths, and explore not just how quantum works, but how it can work for you. So for the past few episodes, we've been talking about quantum computers themselves. But today, I want to discuss how people are actually using them as, well, computers. Quantum computers were first conceived as simulators, which would give physicists innate access to the laws of nature itself. And today, some of the most exciting potential use cases of this technology use them for exactly that purpose. So for today's episode, we're going to talk about work that uses quantum to simulate the physics of nature and the universe at the most fundamental level. And by that, I mean the particles and forces that hold atoms themselves together. I'll have two guests on today to discuss that work. First, I'd like to introduce Joana Freixenet Morales, a researcher from IBM Research. Joana holds a physics PhD from the Institute of Photonic Sciences in Spain, where she studied theoretical models of quantum many-body phases of matter. I'll also have on Enrique Rico Ortega, a professor at the University of the Basque Country, currently working at CERN. He's an expert in particle physics who studies the physical behaviors of materials at their surfaces. Together with other researchers, they recently used quantum computers as a way to model the microscopic forces that glue particles together. This research could one day aid physicists using particle accelerators to try and understand the universe at the most fundamental level. Hello, Joana, and hello, Enrique. How is it going?
Hello.
Good.
Nice to meet you guys in person in web world. So I think I want to just get started talking about studying the universe. And maybe we can start with you, Enrique, how you got into this field and, why you're excited about it.
Well, nowadays there are times that are really impressive of many changes with the eruption of these new technologies, all these quantum machines, and they give us the possibility to study physics in different ways. And this is what we wanted to start to do with this IBM machine. And one of the questions that we have is how to understand physics at the most microscopic level using this type of machines.
Cool. Well, maybe we need to get started at the real basics, and that's what's an atom and what's inside of it.
Initially, in the old time, the people thought that the atom is the tiniest piece of matter that you can get. But we know nowadays that this is not the case. That this is a composed particle, and is made out of a nucleus, and then surrounded by a cloud of electronic cloud by electrons. And within this nucleus, we also know that the nucleus is not just a particle. It's also composed of some other particles, protons or neutrons. And within this proton and neutrons are even smaller particles and forces that keep this neutron and proton together. There are the quarks, there are the glue, and these are these strong forces that are studied here at CERN, where I am working. Our question was, can we realize, can we mimic, can we emulate in some way, some form, all of this physics in a quantum device, in a quantum simulator, in a quantum machine? And this is what drives us to use the IBM quantum computer.
Well, so how are we studying the physics of particles and quarks and gluons today?
Well, there are obviously this is a big field, and since many decades ago, but the people are studying these things with analytic tools, some perturbative methods, with more numerical tools. Usually, they're using big supercomputers and Monte Carlo techniques, and nowadays, with these new machines, this is what we are proposing: having a new tool that could explore some other scenario that cannot be analyzed or with these perturbative methods or with these Monte Carlo classical methods.
Got it. So basically today, at least on computers, we have a variety of these kind of, you said perturbative and Monte Carlo methods. So kind of these methods that rely on, let's say, a bit of randomness and, kind of the best models of computing that we really have in order to simulate what might happen at this fundamental level. Is that making sense?
Yeah, you could say something like yeah.
Cool. And if I'm wrong, you could just tell me I'm wrong, because I'm definitely wrong a lot more than I hope to be.
Okay.
Maybe to say a bit more about this, we're just relying on approximations. And in some cases, these approximations fail. We need to simulate simpler models than the ones that really exist in the universe. So then you're very limited. And in some cases, you know that if you want to go beyond the approximation, classical methods like the ones that Enrique mentioned are not going to work.
And how about you, Joanna? Maybe I can get some background on you and your role as well.
Yes, sure. So, well, as you mentioned before, I did my PhD at the Institute of Photonic Sciences, and there I was studying many body more like quantum systems. And this is a very abstract general term, but it includes different models that are used to study materials or, for example, for high energy physics. And from there, I drifted a bit towards quantum algorithms and quantum computing. Now at IBM, I'm studying with people that are doing different types of projects, some more related to optimization or to quantum chemistry. But in fact, the project that we're going to be talking today, I think it's one of the most exciting. And for me, it's very close to my heart because in the PhD, I was doing things similar to that. So I'm coming more from the quantum side, but let's say I'm also very interested in what's being researched in particle physics. And as Enrique said, I think it's a very interesting moment.
Joanna, you were saying that these are simplifications of nature. We're using computing, Monte Carlo methods. And so can you give me a little bit of sense of like the process for a physicist? Neither of you can answer this. Like when because I understand studying particle physics as like Large Hadron Colliders, but clearly there's like a big computational element of it as well, right?
Yeah, so there's different levels of approximations that need to be made, right? So we have reality. We want to understand how particles behave in the universe. And then there's two ways of studying this. Usually, I mean, in science, we have, on one hand, we need mathematical models that describe this, and then being able to understand them, simulate them, compute them. And then on the other hand, we need experiments that connect to these mathematical models so that we can prove that the things that we're calculating are actually the things that are happening in reality. So about this experimental part, maybe Enrique can tell you a bit more about this because it happens in CERN mostly. But about the theoretical part, we need like the models that could simulate reality are, for example, in 3 dimensions. We know that the quarks that Enrique was describing at the beginning, they interact using some forces that are pretty complicated. So you need very complicated models to describe them. And then first of all, in some of the models that we're studying, we're reducing the number of dimensions. So for example, the project that we did happens in 2 dimensions. We're changing a bit the type of interaction so that they become simpler. Then you could start approaching this with classical techniques, but some of them even then still fail. And then what we did here is we were able to study the evolution and how these models behave. Maybe later we can go into more detail with quantum computers.
Cool. So then for this one, we're trying to simulate the universe with the laws that it actually follows. But obviously that's really hard. So the rules that we're trying to simulate here is, how atoms, especially like quarks, the smallest constituent pieces of protons and neutrons are being glued together, right, with these gluons. And so I suppose what you're saying is then we can study these. It's really hard to study these classically, but there's a way to simplify them, like going into 2 dimensions instead of 3 dimensions. Is that right?
This is one of the approximations.
So what you are saying is that our universe, really the one that we are trying to study in these quantum machines, is a really simplified universe. We are trying to extract basic features that we want to understand about nature. Nature is obviously much more complicated than the need of the experiments that are happening here in the LHC at CERN, obviously. But to understand processes that are not completely well under control or they are not understandable, we simplify the models. And this is what we do now in this work that we have realized in the IBM machine, going, as Joanna said, to a 2-dimensional system and with a model that is describing the interaction that happened between the quarks. That is a simplified model, and even our quarks is something also much more simple. That is what's going on in nature. But still has enough physics to understand some particular aspect that we want to know about the microscopic world.
Got it. So why is it that this stuff doesn't just show up when you're trying to do the particle collider experiments?
It happens, but now what happens with these quantum machines, with the IBM machine, is that you have much more degrees of control and freedom. Nature is given. the mass of the particles is the mass of the particle. The coupling of that are coupled with the particles are given, and this you are not going to change because you test nature, and this is what it is, and you need to understand nature within these given parameters. What we can do now is simulate nature, change this parameter, and what happens if we change the mass of the particle? What happens if we change the coupling constant of this interaction? And obviously, again, within our simplified model, we try to see something that mimics the actual physics that happen in these colliders.
Maybe stealing the words that I heard Enrique say once, but like we're trying. Building all these colliders is also very expensive. I think it's necessary because you need to connect these models and the simulation of these models to reality. But here we're really able to simulate what happens in some kind of tabletop experiment. So it's much smaller devices that we're using where we can play with the parameters. And as he was saying, we have simplified models, but we can look at very different situations. And this is this is also what we do with normal computers when we're trying to simulate, I don't know, how the wind behaves or like this kind of simulators of situations that happen in reality. And this allows you to study things in a much more complete way, let's say. So, yeah.
Okay, I think I get it. So it's like you are able to, like, what we're trying to do is understand nature. And so, sure, you can kind of recreate these conditions in a particle collider, and measure the mass and measure the energy and things like that. But where we need to sort of uncover the sort of, if we could actually reproduce these processes and sort of predict them, then it kind of gives us like a really good underpinning, almost like a mathematical basis of what's going on. So if we can start with these simplified models computationally, then it gives us like that good, almost like we can create a hypothesis that we can then test with the Large Hadron Collider, right?
Exactly, yeah. And this is what physics does at the core. Like it does this we're doing it with high energy physics, but in general, we want to have simplified models of reality to test if they work. No,
in a way, you isolate from nature what you don't understand, and this question that you don't understand from nature, you don't take the whole nature and you try to simulate it, but it's just this aspect, and you try to simulate this aspect and try to change the conditions and try to understand it in different conditions. And in this way, you can try to prove these things that you are trying to looking for.
I see. So we're not just like studying the entirety of physics at once, but it's this specific element, which is how do quarks glue together, and being able to just focus on this as a simplified model and then kind of use that to then help build out your sort of broader theory of the universe. What makes this a problem that's well suited for quantum computers? It might actually be obvious to readers like, oh, well, they're particles, they obey quantum physics, and so, can't you just do it on a quantum computer? So I'd love to hear a bit more about the actual details of like why this is a good problem for quantum computers and why it's maybe not as simple as people think it is.
Okay, I think this is obviously we are not in the mind of Richard Feynman, but this was in the imagination and in the dream of Richard Feynman, to make nature to simulate itself. And this is what we are trying to do. So the first thing that we need to do to simulate nature, obviously, is our building blocks has to behave quantum mechanically, because we know that nature at the microscopic level, in the laws that govern microscopic world, is quantum mechanics. And now what we are doing is introducing some interaction, some evolution that this is mimicking what's going on here in this big collider. So it's really inside this nucleus that we were saying about the atom. Why these machines are specifically well suited for that? Because they are built out of quantum resources. The degrees of freedom of this IBM machine is a quantum element. So this is going to mimic our quantum particles, and on top of it, and this is something completely new with respect to the other method that we were mentioning, can follow the time evolution, the evolution in time, in real time, of the whole description of our system. This is something very, very complicated with the method that we have it till now, and this is a huge avenue that now the new machines are opening. So we can have our degrees of freedom, our quantum degrees of freedom, and see how evolve in time and how they behave. And this is exactly what we did in our work.
I see. So it's really like this is the dream of quantum computing, that we have a system that acts quantumly, we have a world that acts quantumly, and so this is like a perfect example of taking our quantum world and then using a quantum system to study it.
Yes, and maybe I would go even further in the sense that there's different models that are quantum that are worth studying with quantum computers. People are looking at molecules, people are looking at materials, people are looking at different types of models that follow this idea, let's say, of Richard Feynman that Enrique was mentioning. In this particular case, I think it was very well suited for the kind of devices that we have now, because on one hand, when we simplify these models of the universe, we're putting them in, we're discretizing time and space. And then we have some kind of lattice of discretized points that interact with the neighbors. And if you look at IBM machines, they're built in 2 dimensions, and you have connections of these qubits in 2 dimensions. So then we can map this evolution, like the interactions that are going to define the evolution, to the quantum circuit that it's going to happen in this device. And on top of this, the kind of models that we're studying, they have some requirements, some symmetries that need to be fulfilled at all times. And something very nice that we've done in this project is that we've used these symmetries as some kind of error mitigation technique. And what this means is that we're looking at the results of our quantum computer, and we are able to check, looking the symmetries, if they're correct or not. This is maybe something we can enter in later, but quantum computers have noise. And in this model, we could use the model itself to kind of get some correction of this noise. So there's many different models. In particular, falls into this category of simulation of quantum systems. And then on top, I think it's one of the cases in which we really made something targeted for what we have now. So that's very nice.
So it actually is kind of profound here, right? Is that we're trying to study this specific simplification we're studying is this kind of 2-dimensional simulation of particles on a flat surface, basically. And so because of that, we can almost do this one-to-one mapping, right? There, where like the quarks themselves are represented by qubits, and then the glue is represented by qubits, and then creating basically almost an exact like analog model of what we're trying to simulate as our simplification of nature, and then just run it on a quantum computer. So you're saying time evolution, like the clock ticks on our quantum computer forward, and hopefully what we're creating is a system that acts the same as this theoretical model of the universe that we're trying to study. Is that right?
Yes.
Exactly. Imagine that we will manage to go really deep in this nucleus that we were saying in the atom, but really inside with these quarks and glue, and see what is the dynamics there and try to understand what's all of this there. So what we are doing this is coming and bring all this physics to the IBM machine. I try to simulate this in what's going on there inside of this at this microscopic level.
And experiments like the ones that happen in CERN only allow you to get some information once the particles have collided, and then it's also very difficult to track this information and extract out of there to understand what's happening. Here we have access at the whole system, and we can measure at every time step and see what these quarks are doing and how they're interacting. So it gives you a lot more vision on the system.
And now I do want to get into the noise piece, because this is actually what makes this so exciting, right? Is that, I know that quantum computers today are noisy. They don't do exactly what we want them to do. And so the result is we end up with these errors where we think the qubit should be a 1, and then you measure it and it was a 0, even though you wanted it to be a 1. But this is such a cool experiment because you've figured out a way to make this run even in the presence of all of this noise without error correction. So you started to get into that, but I'd like to hear a bit more about, what are these symmetries and how is this actual like error fixing work?
Well, and there was some plethora of methods about error mitigation and error correction that IBM also was developing. But within this work, we created new ones because the system we were studying. There is some local symmetries that fulfill this model. These local symmetries are called gate symmetries. This is like a basic building block for the whole structure of nature. Gate symmetries is building this type of symmetries. And this is just a symmetry that is local. If you violate this symmetry, and you can check it locally in a group of qubits that you were describing, if you don't fulfill these things, immediately there will be a red flag. And this is something that we were checking in the evolution. There was a flag when this is not fulfilled, and we were recovering this type of errors. So thanks to the symmetries of the model, we could also impose this type of new techniques of error correction.
When you first learn about the word symmetry, it's just like, oh, this thing is its mirror image. But actually, we're not referring to that, right? We're referring to that, like, there's like, it's like a repeating lattice. So the stuff should be the same if I look in this quadrant as it should in a different quadrant. And so what you're saying then, if I'm understanding you correctly, is that you can basically find these matches, that if something is different in a different part of the experiment than it is in or two different places in the experiment, then it's violating this symmetry, which we know nature requires the symmetry to exist. It's like having a fence of rectangles where one of it is suddenly a circle. You're like, oh, well, that's obviously an error because I know this is a fence of rectangles. Does that make sense?
Kind of. So, and in a sense, our whole model, following your idea, has to be a bunch of rectangles. And in the whole evolution, these rectangles are doing things. Suddenly, there is a circle or there is a star. Oh, there is an error there. And because of this symmetry, we can detect it and we can correct it. But these are obviously in these patches, in these different places, we can check out these possible errors.
Yeah, maybe what you were mentioning connects more to translation, what we call translational symmetry. That means that in different parts of your model, things should be the same. Here, it's another type of symmetry, but it's looking locally at these qubits, and some things have to be always the same or in similar configurations. And if there's one that doesn't match these configurations, it means it's violating this symmetry and it's something that cannot exist. But yeah, there's different types of symmetries. There's local ones, global ones, and then this can become very, very technical. But yeah.
Yeah, so there's basically even simpler is there's just something innate about the qubits themselves, like basically mathematical properties that we know just need to be the same between the qubits, or need to be sort of this, like what we predict them to be. And if they're different, then it's an error.
Yes.
Exactly.
Cool. It's even simpler than I said.
And it's because we are studying this system that is trying to describe this microscopic model, the nature at the most microscopic level, is when these symmetries are relevant. Because again, the whole structure that we understand now, how it works in this nature, is built out of these symmetries, out of the symmetries that allow us to do error correction. So this is really amazing.
So these symmetries, if you want to imagine them a bit better, you have these qubits that are particles in your lattice, and they're connected by these fluxes that corresponds to the interaction between the qubits. This symmetry kind of tells you that you cannot have qubits that are isolated where these fluxes don't appear. Like you cannot have this kind of strings ending in nothing. Like there's things there that cannot happen because they're not possible. So that's why these symmetries are kind of playing with this idea, and then that's why they need to be fulfilled. Otherwise, you would have states and you would have particles that don't behave as the. I don't know if this is a good metaphor, maybe.
No, this is actually perfect.
Confirm or deny.
No, this is perfect. Right?
Okay.
Because this is the thing, and this is actually, we didn't get to this, but this is the whole thing that we're trying to study, right? Is that there's like quarks are glued together in atoms. Like you can't just have a quark sitting on its own. That's the whole idea of this kind of strong force of nature, right? And so as you pull these quarks apart, like, in fact, the force between them kind of gets stronger, like it's literally glue. So this makes sense, right? If you're simulating this thing on your quantum computer, like you can't just have a qubit sitting on its own, because then it's like violating the force that we're trying to study. It's like a basic thing. Like, no, it doesn't work like that. So that's an error.
Exactly. Yeah,
amazing.
Exactly.
Yes. That's how it works.
Can we get deeper into this? Like, it's kind of weird that quarks don't just sit around on their own, right?
It's not so weird because we know that we are getting used to electrons, and you have an electron. It's a particle, but we know that with an electron there is always a radiation, that is the electromagnetic field. So out of an electron is not alone. There is always some radiation. What's happening with these particles that we are trying to understand, the quarks, is that this radiation is really concentrated in thin strings that connect a quark with an antiquark, a particle with an antiparticle. And And trying to pull this apart, this thin string is getting stronger and stronger, so it's costing more and more energy. And this is what creates that these two particles, we can never pull it apart, but it has to live together. And this is the notion of confinement, and this is one of the properties that I wanted to address and to characterize within this model.
Got it. So basically, just by trying to pull these things apart, you're like injecting them with more energy, and now it just makes the string kind of even more good at being glue.
The thing is that as you insert more and more energy, there's a moment that this would be too much energy. In fact, what happens, and this is something we didn't look at in this particular paper, but a lot of people in the community are looking into this, is that if you keep pulling these particles apart, you could end up breaking the string, but because you have so much energy in there that you create two new particles. So then there's going to be two pairs of particles that are connected by strings, and they're never left alone. These quarks are always going to be in pairs. But yeah, when you start pulling a lot, instead of separating, you create new particles.
This is really cool. This is like this is literally equals mc squared, right? Like I put all this energy into these particles, and then suddenly the energy just literally turns into more particles because the particles aren't allowed to be pulled apart. But this has like some cool implications, right? Doesn't this mean that like if I put in like a ton of energy, I can just get these like big jets of particles that just come shooting out and just like a bunch of matter that I've suddenly created?
You are just describing a collider.
This is what happens at CERN. Yeah,
exactly. They are putting a lot of energy in these particles that they are in this collider. They make it a smash, and out of this smashing of particles, they create all these jets. Analyzing all of the physics is really a huge endeavor. As we said, there are many techniques, and now we are offering, or we think there is a possibility of a new tool that is quantum machines.
Yeah, but I would say it's not so easy to create all this mass out of the energy, because in this like E equals mc squared, this c squared is quite a big number. So you really need to put a lot of energy to create new mass. And that's why CERN and colliders are very, very expensive. Yeah.
I thought you physicists just treat c squared as 1.
Yeah, just a constant. Doesn't matter.
Okay, so you really need, this is the kind of fundamental part of this whole thing. Like, you actually need to have a giant particle collider because of the c squared and equals mc squared. Like, you need to put a whole lot of energy into a particle accelerator in order to really study what's happening at this physical level. So I could do that, or I could run it on a quantum computer.
Models that are simplified models. And again, this is nice that this thing, as you said about the energy, is if you're going to go to smaller and smaller distances, we have to put more and more energy. This is a funny thing of quantum mechanics. So the smaller we want to understand, the more energy we have to put. And that's why we need to build these huge colliders.
Cool. And so this is one last... Okay, so the people who don't see the video right now, who are just listening, I am indeed wearing a CERN sweatshirt. I think particle physics is really cool, and so I'm really excited to talk to these folks about this for that reason. And so I want to talk about like one final thing that I'm really excited about, which is that I know for a fact that if you put enough energy in, at some point it stops being like crazy particle jets of energy and actually just turns into like a soup of a bunch of quarks connected by strings. Is there a way to run this this quantum simulation kind of to a point that you can begin to study this sort of quark gluon plasma quark soup type thing?
These are experiments that are a really complicated experiment. And why they are complicated experiments? Because they require many different energy scales and many different time scales and length scales. This question of the quark gluon plasma is a huge issue, as a huge problem here at CERN. And again, aspects of this problem maybe we can tackle with the quantum simulator, but we have to be humble. There will be only some aspect of the whole process, but because the whole process is really complicated, involve many length scales, many energy scales or time scales. Yeah.
Got it. So maybe we need a slightly bigger quantum computer to really study the like fundamental questions of how the universe acted a fraction of a second after the Big Bang. Slightly bigger quantum computer.
Yeah.
Slightly bigger, maybe.
And less noisy.
And less noisy.
And less noisy.
Yeah, that's important.
Yeah.
So this is a great segue into kind of one of the important things that we should talk about, right? Which is that, this is still a simplification of nature, and so therefore it is different from the way that nature actually works. So maybe I have a two-part question, and we'll just start with part one, which is like, okay, so why is this a good approximation of nature? Like, why do we feel confident about this as sort of a way to understand the world?
Partially, we understand some things. It's not that we understand the world and we understand nature. We took a model that has a particular property that has confinement in it, meaning confinement that there are never there will be two particles far apart. All the thing we were mentioning about the strings, about the particle antiparticle, and so on and so forth. So this is a very toy model. And we're within this toy model, we know that this is feature. We want to understand them much better. And specifically, what we were checking is was about the time evolution, how the system evolved and how these strings evolve. We are changing some parameters.
And I think what's important too is that in physics we do controlled approximations. Like you start with a model that would describe the totality of things. You know how this would kind of look like. And then you start by saying, okay, actually, if we can assume this to be discretized, but you know that if I take this number to infinity or if I have infinite resources, this would be the right solution. But then I'm going to something a bit simpler. And then I'm reducing the number of dimensions, but taking into account that this, if I increase the number of dimensions, it matches to what it should be. And then I'm also, like when we're doing time evolution, since we're doing it in a quantum circuit, we're not doing exact time evolution. We're building circuits with some gates that emulate this time evolution. But we also do it in a controlled way that we know that if we would be able to run infinite circuits, this would match exactly what we would be doing, but then we reduce this. So then it's always these controlled approximations, and then you end up with a simpler model, and this is what you do. And then at the moment that we start having more resources, better quantum computers, then you can start maybe reducing some, like getting rid of some of the approximations, like simulating something in more dimensions, maybe simulating something with better symmetries, because here when we say simplified model is because we're doing a bit of different particles to what quarks really are. And then we would know which directions to take once we have the resources. But now we've used this model. Yeah.
I think this is actually, the word toy model is really maybe a useful kind of route to understand this. And let's just like port this over to games. Like if you're trying to make a video game, like you can start with just the lowest amount of resources and create a game where you're sort of just in 2 dimensions, like running, and you can introduce some basic physics that allows you to jump, right? And like that exact game can do a really good job studying running and jumping. And it could even help like predict what might happen at the most basic level if you like run into a wall or if you jump off of a ledge. But then like what you have to do is, as you sort of get more resources, maybe like as video games improve, you have access to better GPUs, to better CPUs, and suddenly you can start introducing new elements to your video game. I can introduce a third dimension. I can introduce like different textures and surfaces and, light and magnets and all sorts of stuff, and then slowly build up your simulation to be more and more accurate to the way that the world works until it's like 2025 and I can play like the latest Halo game or, I don't know. I don't play enough video games to have a good example here. But like a video game that actually simulates the world really well. And so it's almost like exactly where we're at with quantum computers is that, today we're sort of maybe at this level where I've created like Super Mario Brothers, but for studying the strong force. And now one day we're going to have like Super Mario 64 for studying the strong force. And then, Super Mario Galaxy on the latest Nintendo system for studying the universe or something like that, right?
I think it's a good analogy. I've never heard it before. But
You just create it.
Amazing. I promise I sort of understand what I'm talking about, but maybe I can't actually promise that at all. All right. Actually, no, I do understand because now I want to ask you my next question. So, okay, if we're today at Super Mario, the very first Mario game, but it's quantum computers for studying the strong force, then how do you kind of scale up your game to get to this point where we're beginning to have it simulate a universe that more closely looks like the universe that we live in?
So as you said, these are prototypes. And they are prototyped initially with some basic elements. Okay, now we have to put more features in it, as you said before. So for the moment, we have the simplest symmetry that we can imagine with this local symmetry that we were thinking. Can we simulate something more complicated? Because we know that the symmetries that are in nature, one of the worries that the one that we were studying is a abelian model. In nature, we know that it's non-abelian models. It's more complicated features. The particles, our quarks, they are bosonic particles. Can we introduce particles that behave like fermions, like the quarks, like they happen in nature? So all of these are levels of complexity that out of this basic prototype, we can start to increase these difficulties and try to simulate more and more and go closer and closer to these big colliders. Again, I think for this new feature, we have to be humble. We have to look at this approximation. We have to look at these toy models, and probably even in the medium term or in the long term, still we can only isolate some partial questions to the whole answer, because, as I said, these are huge questions with many different aspects of these time scales, energy scales, length scales, that only nature. Imagine one day we have all the elements in our quantum machines, but if we have all the elements of the quantum machine, we have nature. So it's nature who is giving us these things. So that's why also we are only restricted to some aspects, because if we have all the elements, it's because we have nature itself.
Yeah, I think that the boson fermion thing is important for folks to understand, which is simply that, like, the simplification that is being run by y'all here, it's almost like if you imagine a checkerboard where on each place of the checkerboard there's a photon sitting there. Now, a photon obviously acts like fundamentally different from the way that a matter particle like an electron or a quark would act. And so, but we can today on a quantum computer, we can simulate the checkerboard of photons. So we're simulating the checkerboard of photons that are interacting in the way with these kind of glue particles between them. And so kind of, it sounds like the next step of the simulation is, can we start to introduce mathematics to this sort of checkerboard of photons that first makes it actually more like a checkerboard of quarks, and then from there make it more like add more stuff, just like more mathematics and more physical laws and things to make it begin getting closer and closer to the way the universe actually works.
We are in a white and black world. We need to go to the color world. So you want to know the analogy?
Amazing. 3D chess. 3D.
Exactly.
We're playing 2D checkers and we got to learn how to play 3D chess.
Yeah, but even if it sounds frustrating because we're very far from simulating reality, already with these simplified models, you can find very interesting things that can be very important to understand the fundamental forces of nature at the end. So just to put a positive note on all this, I mean, it is, yeah.
The whole thing is positive. I think it's really cool. And actually, it's like exactly what I want to ask is that, like, the thing we're not really saying here is that innately, the same way that with, like, as we get more computational resources, we can make better predictions. Like, these are useful models. It's like people talk about quantum computing being useful. Like, these kinds of things are useful to you guys, right? Like what are you actually, like, you're learning things by making these models.
We are learning nowadays how to use these machines to do these kind of simulations. So yeah, so I think it's a learning process, and in the same way, this machine is getting better and better. So this is a win-win situation.
Yeah, exactly. Like, the machines are advancing, and on the other hand, we're getting better and better on, like, thinking which is the best way to map things in the machine, which techniques we should use, how we should run this, and all of this takes time and practice and getting used to the hardware and, like, figuring out. And in this project, we spend a lot of time. Like, this is something we've commented internally many times. Like, there's the part of, like, okay, this is the physics we want to study, and then a lot of time really figuring out how do we map this, how do we use the machines, how do we get the results, and then you can share this knowledge also with the community, and different people are working on these things so that we all start to understand what things we can do right now.
Now, in the future, like, let's say that you had access to a quantum computer with, 200 or 2,000 or 20,000 qubits that can operate, on the scale with basically without error, that can do exactly what you want them to do. How do you, what is the sort of process? What are you hoping to study? And what is the sort of back and forth between the quantum computer and, like, the experimental world look like?
Recently, we have just here a meeting in that CERN that we were discussing exactly this topic. You have access to this machine. What do you want to study? And again, we have the two ways of thinking, and I think the two ways has to be explored. First, still is to take the things that you don't understand so well, isolate these questions, and build some toy model within that is a hand of your for your machine, and handle this question that you want to do. The second is advancing in putting all these ingredients that we were saying about the going from the black and white to the color. So can we put these non-abelian symmetries that we were referring to? Can we put all these fermionic system in these machines? Can we go closer with how nature really behaves? And I think these two ways of analyzing these problems, I think they are valid, and this will be, I think, how we are going to evolve in the community.
Yeah, and having access to error correction, like in this latest work that we've done, we were very limited by noise. Like we've really struggled to get some things out because noise at the end really limits the time scales that you can evolve the system, the kind of things that you can implement. But as these things become better and better, we're gonna see new implementations, and for sure there's more physics that you can observe, a lot more than we were observing right now. We're already excited that there's like at some point more connections, and like the hardware is slowly changing, and at some point where there's a correction even more.
Well, okay, so I have two final questions for you both. And the first is like, it sounds like we're already using quantum computers to kind of do some interesting studying of the universe. It also kind of sounds like the ideal future of this is being able to like accurately implement laws that are kind of getting closer and closer to the world that we live in, so that we can actually make predictions, right? That the quantum computer is going to tell us things that we don't already know. So do you have a sense of like maybe when that's going to happen, and even like what size quantum computer you might need to start to kind of flip the script a little bit there?
I mean, the kind of sizes you were talking about, if you have access to thousands of qubits, and I think even more it's good to have access to many qubits, because then in order to connect them and so on, I mean, you also have more freedom. But mainly, I think error correction is going to make the big change, like having qubits that are like logical qubits that are error-free. And once we start having access to this, we also I mean, in these cases, to simulate the evolution of certain systems is something that we know how to do with the algorithms that we were using here. In other fields, or also to study different features, we might still have to come up with the right algorithms. So there's research also on the algorithm side that it's being done as we speak, like together with the hardware side. But yeah, once we have access to this, I think, and we're gonna start discovering new physics that it's gonna. I mean, we're already kind of. From IBM, we talk about this utility era and so on, which means that, and we've shown in our paper that the results we get from the quantum computers start competing really with the best state-of-the-art classical techniques. In this case, in the collaboration, there were a team of researchers that are really experts on using, in this case, tensor networks, using like a lot of computational resources, doing things like if you take the people that are know better how to do this with classical computers, and then you take the quantum computer, we were like kind of taking this as a benchmark, and we were not showing advantage over this, but we're still at a level that these things can start to be comparable. And now at some point, we're going to see that we can start discovering things that we couldn't access before.
Okay. Well, so this is awesome. And now I wanted to ask you to basically I love asking this question, and I feel like I already know the answer for you all, but what do you hope a world with quantum computing will look like?
Do you want to start? Or?
Even there is no, because this obviously involves many things, this even geopolitical stuff and so on, because you know that with the access to a quantum computer, you could break some security message and so on and so forth. So even that we don't have a complete quantum computer, in this business about security, they are already changing. There's already some changes, because obviously they are thinking in a post-quantum situation. They have to be safe about the possibility that they break these messages. So even without a quantum computer, already the world is changing. And when we have a computer, predicting things is always complicated. The people in IBM know that they were thinking that there will be only 5 clients to sell computers in the classical computers in the whole world, or something like that. Was in the fictive. Someone in IBM was saying something like this. So predicting what can happen with a quantum computer is complicated. From a research I hope, or I think, I'm pretty sure that it's going to be a new tool for studying this complicated many-body system and this in particle physics, or is in material science, or if it's in quantum chemistry. We will have a new tool. A new tool will give us a new access to new questions, and then we can analyze all these problems in a new perspective.
And Joanna, what do you hope a world with quantum computing would look like?
So I agree. It's a difficult question to answer because it's difficult to imagine how this could change. And also the technology, once it starts working, it's also then you start finding new applications. But what I'm most excited about is simulating nature, like simulating high energy physics models and understanding the universe better. But you can also then have access to more information about materials and material science or molecules. So ideally, like a quantum computer with error correction and so on could be a very nice way to simulate all these systems and access information, like try new molecules, new compounds, new materials, see how they behave, understand better different phases of matter. And I think this could be a very big progress for science in general and for different applications if it's used well. And because coming from the field of like understanding many-body physics and this kind of models, classical computers are really limited. Like when we start looking at the models themselves and the mathematical models, you very, very easily reach the top where like you cannot compute more things because it's like too heavy. You need too much processing power. And people are using big supercomputers and so on. But even with that, like we're very limited. So if we start seeing differences in this and being able to do certain things, there's a bunch like of phases of behaviors of like different things that people want to understand, and that it would be very promising.
Well, that's great. I really appreciate you two giving me the time today. This was a really fun conversation. And I hope to talk to you both again soon. Thanks again for coming on.
Same, thanks.
Thanks.
It was very nice.
That's it for this episode of the Coherence Times. If you enjoyed the conversation, please be sure to subscribe wherever you get your podcasts and share it with somebody who is curious about quantum. You can find us on Spotify, Apple Podcasts, and YouTube via the IBM Research Channel. And for more episodes, resources, and deep dives, please visit us at ibm.com/think/podcasts. I'm Ryan Mandelbaum. Thanks for tuning in. And remember, the quantum future isn't just coming, we're building it right now.